All right, let's go ahead and get started. So I'm Julia Matevosyan, Chief Engineer at Energy Systems Integration Group. ESIG serves in leadership role with the Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scale and speed. This is being done by providing coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across 5 action pillars. The foundation of G-PST is a group of 6 power system operators from around the globe who are facing high penetration of wind and solar inverter-based resources sooner than other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support, and open data and tools. ESIG is a lead on Pillar 1, and more information on Global Power System Transformation Consortium can be found at www.globalpst.org. As the lead on Pillar 1, ESIG would like to welcome you to this June webinar, which is our joint G-PST Pillar 1 ESIG webinar series. This series is in addition to regular ESIG monthly webinar series and focuses on G-PST research agenda and associated topics being addressed in Pillar 1. Topics are presented both by founding system operators and other advanced system operators active in Pillar 1, as well as members of industry and academia participating in activities of Research Agenda Group and Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of G-PST are also being provided on monthly basis through National Renewable Energy Lab, or NREL. For those of you who would like to learn more about G-PST and how to engage, please go to www.globalpst.org and click on Get Involved tab. Further information on ESIG can be found on www.esig.energy. Next, I would like to go over a few logistical matters before we get started with our webinar. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distraction. For the Q&A, we use Slido platform at slido.com. You need to open browser window, go to slido.com and enter code ESIG30. The instructions are also at the bottom of the screen. You will see a thumbs up button next to the question on Slido, and you can use it to cast a vote and prioritize questions that were already submitted. We plan to save about 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar. So please don't be afraid to ask your questions through Slido. Okay, so today our webinar is going to cover impedance scan tools for stability analysis of high IBR grids. This is a topic which is gaining increasing interest in research community and industry in power systems with high shares of inverter-based resources. Today's webinar will feature Shahil Shah, a senior engineer for grid integration at National Renewable Energy Laboratory in Golden, Colorado. For the past 15 years, Shahil has been working on modeling, control, and stability of inverter-based resources and HVDC transmission systems with specific emphasis on impedance-based methods. He is leading several DOE projects at NREL on these topics, and he has led the development of first-of-its-kind impedance measurement system for utility-scale wind turbines and inverters. He recently received ESIG Excellence Award for leadership in the design and analysis of grid-forming inverter systems. He's been actively contributed to IEEE, IEA, ESIG, and SIGRE working groups focusing on stability of power systems with high shares of inverter-based resources. I'm very pleased to have Shahil here with us today. Today's webinar will explore impedance-based methods for stability analysis of grid with high shares of inverter-based resources. The webinar will cover a PSCAD-based impedance scan software tool, an impedance measurement system developed by NREL for analyzing stability of high IBR grids. Case studies will be presented to demonstrate capabilities of these tools and answer questions such as which IBRs are causing oscillations and how much grid forming capability is needed in the system. Okay, so just short reminder, once again, use Slido at slido.com with event code ESIG30 to ask your questions. And without any further ado, let's go ahead and get started. Shahil, and I'll turn it over to you.
Thank you, Julia, for the introduction. And I would like to thank ESIG and G-PST for giving this opportunity. Let me share my screen. Julia, can you confirm that you are able to see my screen?
Yes.
Yeah, so hello, everyone. Welcome to this webinar on impedance scan tools for stability analysis of IBR grids. I would like to thank you all for taking time to listen to me. And I'm going to talk about impedance scan tools in general and also the developments that we have made at NREL. And for that, I would like to thank our sponsor, Wind Energy Technologies Office of the US Department of Energy. So whatever you see in this presentation, basically that is developed at NREL, that is supported by Wind Office. So we are very thankful to them for that. And impedance scan tools is a really broad topic. So I'm going to really cover where they are used and why they are used, and what they are, like different tools, but not really on how part. I won't focus on how part that much because of the limitation of time. So here is the outline of this talk. First, I'll talk about control interactions and oscillations in IBR grids, then move on to impedance-based stability analysis method for local interactions. So this will be a standard method, which is used for understanding the local interactions. And then I'll talk about scaling the impedance method for system stability analysis, how we can scale that to understand stability of a larger power system with high amounts of inverter-based resources, which is the main topic for today's talk. And then I will talk about NREL's impedance scan software tool. And depending on how much time I have at the end, I'll talk about the impedance measurement system for utility scale wind turbines and inverters that we have developed at NREL. So control interactions, oscillations, or resonance have become very common with more and more power electronics that we are seeing in today's grid. They manifest at different frequencies from a fraction of hertz to several kilohertz, and the waveforms that you are seeing on your screen, they are real measurements. So let me try to find out laser pointers. So for example, here sometimes these control interactions are sporadic in nature. They come and disappear depending on changing operation conditions and because of change in the damping of oscillation modes. So sometimes they are just nuisance. They don't create any disruptions, but sometimes they are disruptive. As for example, in this case, this is a voltage waveform at offshore HVDC converter in an offshore wind power plant in Germany, and the offshore wind plant started interacting with offshore HVDC converter, created this resonance, and which this high frequency resonance damaged the filter capacitors of the offshore HVDC converter. And that wind power plant, which was rated at 700 megawatt, was out of service just because of this resonance for several months. And if I'm not mistaken, I think it was out of service for almost a year. So you can imagine the economic impact that this kind of oscillations can create. Not only the economic impact, they also impact reliability. For example, on this right side, you see subsynchronous oscillation in another offshore wind power plant in UK, which played some role in a countrywide blackout in August 2019. So we need to understand these oscillations or the small signal stability issues. As power system engineers, we try to classify them as depending on the frequency or depending on which equipment is involved. We call it subsynchronous oscillations, subsynchronous resonance, harmonic oscillations, control interactions. But basically they are all same. The classification helps because uh, many times for that particular problem, the mechanisms are common, but sometimes it also creates confusion because the reason behind these oscillations tend to overlap. And although all these oscillations, they look quite different. One thing common for the oscillations that you are seeing here is that what I call them, they are local interactions. So although these oscillations can be experienced at a bigger part of the system, but for these local interactions, we can always divide the network into like a two parts where if we dig down enough, we can show that these are really oscillations between one part of the system against another part. For example, in this ERCOT case, the type 3 wind power plant is oscillating against a series compensated transmission line, or whereas in this offshore, in this case in Germany, the offshore wind power plant is oscillating against an HVDC converter. So in the local interactions, they are easy to analyze because it's one system's one part of the network against another part of the network, and they're easy to mitigate also. Once you understand that, we can develop mitigation solutions. For example, here in subsynchronous oscillations in China, the oscillations disappeared once the protection bypassed the series capacitors, albeit with after the major portion of wind generation was lost. So for local interaction, although the industry is still learning how to mitigate this problem and how to develop standards or best practices, but we already have tools to analyze them or understand them. The second issue that we are seeing, which is becoming more common, is system-wide oscillations, and which are something that we hardly understand. They have become more common in the last 2 or 3 years. For example, on the left side, you see 7 hertz and 19 hertz oscillations that have been appearing regularly in Australian power systems operated by AMO. In the middle, we see the 8 hertz oscillation in Scotland, which were presented by Julian Leslie just in the similar ESIG G-PST webinar a few months back. And these oscillations were, the magnitude was like around 70 kV. So they are huge and they can disrupt the power systems. Several EMT studies done to understand how we can operate power systems with large amount of IBRs approaching 100% have also shown that oscillations or small signal stability can be a huge barrier in achieving that goal. For example, this study from electronics on operating Hawaiian Islands with 100% IBRs showed this problem. So whenever a system planner sees this problem in EMT simulations or a system operator sees them in the field, the question is, where these oscillations are coming from, which IBRs are creating them. Is it like one or two specific IBRs are resulting that, and can we curtail some of the IBRs to eliminate these oscillations? Which IBRs must be curtailed? Is it possible? How to identify an inverter-based resource or a substation in the network where we can put some damping solution? So these are all questions faced by system planner and operators as we transition to include large amount of inverter-based resources. And that is where impedance scan tools can be really useful. So before talking about the tools to understand these oscillations or small signal stability issues, I would like to talk about what are the causes, why we are seeing them more frequently now. And there are two main reasons. One is fast, complex, and diverse IBR controls. Fast means the controls of inverter-based resources, they span from a fraction of hertz to a couple of kilohertz. So their bandwidths, they are all over the place compared to synchronous generators where the control bandwidths were limited. So we have very fast and dynamic rich devices that we are continuously adding to our power systems. They are complex. It's hard to describe this behavior by a few differential equations, which we are able to do with, or which we can do with synchronous generators. So they are highly complex and they are diverse. Each manufacturer will have their own set of control codes, and if not thousands, but few hundred lines of code decide how these inverters based resources behave during different grid events. So the complex controls is one part of the problem, and the second part is declining system strength. With reduced system strength, the dynamics of all these IBRs, it gets coupled, and that is the reason why we see these oscillation issues. Stability analysis is challenging with IBR grids because of, again, complex dynamics of IBRs and unavailability of open box models from vendors. Even in future, if we can standardize the controls of all these IBRs, which might be unlikely, but even if we achieve that, we are not going to eliminate the complex dynamics. So we'll have to forget about the world where we can define the dynamics of our generators by 10, 15 differential equations. So the problem is quite complicated to understand small signal stability of power systems today. So has this problem been solved elsewhere? Yes, mechanical engineers, they solve this problem every day. They also have similar issue. The mechanical structures are complex with complex geometry and material properties, which are hard to model by equation-based models. And they have to rely either on measurements or on doing finite element simulations. So, so the solution that they have developed is model analysis tools, where you excite the structure at different frequencies by some vibration mechanism and then measure the response at different points. We use this data to understand what are the oscillation modes in the system, what is the damping of different modes, what part of the structure is participating in what mode, and how to design a damping solution. So that has been done by mechanical engineers. And we have a similar method in power systems, which is impedance-based stability analysis, which is what I'm going to talk about today. So what you see on your screen is basically the standard approach of impedance-based stability analysis. Uh, if we have an inverter-based resource with the output impedance of Zi, which really represents the impedance not just at fundamental frequency, but for a broad frequency range. And if that is connected to a grid with internal impedance ZZ, then we can represent IBR by a Norton equivalent circuit, or basically a steady state current source in parallel with the inverter impedance, and grid by a Thevenin equivalent circuit or a voltage source in series with the grid impedance. When we find out the relation between voltages and currents for the simple circuit, we realize that connecting an inverter-based resource with the grid creates a negative feedback loop with whose loop gain is ratio of the grid impedance to the inverter or IBR impedance. And we can apply different tools like Nyquist stability analysis or Bode plots. We use that to understand if when the IBR is connected to the grid, whether it will stay stable or not. So the fundamental premise behind this method is that IBR is stable in isolation when when it is connected to a strong grid or ideal grid, and grid is stable without the IBR. And that is the fundamental premise. This is a reasonable assumption to make that an IBR would operate stably when it is connected to a strong grid. So question we ask is, what happens when we connect them together? When IBR is connected to the grid, whether they remain stable or not. So that is the fundamental premise, that IBR and grid are separately stable. What happens when we connect them with each other? And this approach has been finding a lot of applications. ERCOT is using it to understand, and many other system operators are using it to understand risk of subsynchronous resonance between type 3 wind power plants and series compensated transmission lines. Many utilities, the vendors in Europe, they are using it to understand stability of offshore HVDC converters, to understand if their offshore HVDC converter will interact in an unstable manner with offshore wind power plant or not. And it is also used in electric traction networks. So this approach to understand local interactions is finding a huge applications. It is going into the standards. We are working with colleagues in Europe to include the impedance measurement of wind turbines in testing standards. And there are also system operators are also developing standards to ask for this impedance responses as part of a connection agreement. The question is, how do we scale this? How do we scale this to understand stability of a large power system? And that is the main topic here. Can we scale this for a large power system? And most researchers, they have followed this usual approach, where we assume that IBRs are stable when they're connected to ideal grid and network is stable without the IBR. And what happens when we connect them together? So for example, here, I'm showing 4 IBRs, and we assume that these 4 IBRs are stable when they're connected to an ideal grid, and then assume that the network is stable without these IBRs. And then the question we ask is, what happens when we connect them? And this usual approach, which is basically based on that standard impedance-based stability analysis, it works fine in theory, but it's not practical, because here we need to scan the impedance of all the IBRs as well as of the network, looking from all the ports of IBR. So for example, here we are seeing 4 ports. So we need to know the impedance of network from those 4 ports, which gives us 4x4 matrix of impedance transfer functions. Now, we know that 3-phase power systems, we has a 2 degree of freedom. So each port actually has impedance, which is a 2x2 matrix. For example, in DQ impedance, we have D axis and Q axis. If we represent impedance in using positive sequence or negative sequence, we have again 2 degrees of freedom. So actually we'll need the impedance of this transmission system as a 8x8 matrix. And now if you think about 10, 20, or 100 IBRs, it will be a humongous task to scan the impedance of all IBRs as well as impedance of the network looking from that all IBRs. So is it possible the way to scale this system? Yes. Does it work? No, it's not scalable. So this is not a practical approach. So to address this challenge, we have developed a new approach, which we call reverse impedance-based stability criterion. And let me use this cartoon on what I mean by that. So this is again the usual approach. If you think of this guy as our system or our network, and the question we ask is whether this system will remain stable or stay on the hill, or it will become unstable and fall down the cliff if we connect all these IBRs to it. So in normal operation, in this approach, we isolate all IBRs, look at the impedance of all IBRs, as well as of this network from those IBRs, and then do the stability analysis. As I mentioned, this is not a scalable approach. So what we do, we turn the problem on its head, and we propose a reversed approach. See, whenever we are doing the stability analysis, either we see oscillations in field or oscillations in EMT study, we start with a stable system. We are never going to analyze a system which is unstable. You can't perform impedance scan. You can't really do anything when the system is already unstable. So we start with a stable system and try to answer questions on how each IBR is playing role when we see these underdamped oscillations. So in this reversed approach, the fundamental premise is that the integrated system is stable. The system is stable with all the IBRs. And then I select a specific IBR and try to answer question on what will happen if I remove this IBR, whether it will make the system unstable. In this case, I need to do the scan of only this IBR and impedance scan of only that IBR and impedance scan of the network looking from that IBR, so only from one port. And we can repeat this process as many times as you like to understand how each IBR is impacting the stability of the network. So earlier, the fundamental premise was that IBR is stable without the grid or without the practical grid, and grid is stable without the IBR. What happens when we connect them? And that approach is not scalable. Here, the approach is that IBR and grid are stable together. IBR is also stable when it is connected to a hypothetical ideal grid. We want to ask question, what will happen to grid if I remove this IBR? And this is also more practical way of looking at stability, because whenever we see oscillations or stability issues, a system planner is not going to, it doesn't want to understand how each IBR in the system are impacting the oscillation modes or stability. We select few IBRs depending on their size, their importance in terms of other stability like frequency stability or voltage stability, how much fault current they contribute. So a system planner wants to know only a few IBRs, like how they impact the system modes. If you are a developer, you want to understand how your plant is impacting the stability. So if tomorrow there's an oscillations and system operator curtails your plant because they think that your plant is creating all these oscillations, you want to know whether that is true or not and how you can improve your controls to damp that. So we always want to understand the impact of few IBRs, and that is why this reverse approach can be helpful. You can just perform the analysis or at a few selected IBRs. So to apply this approach, we have developed a software tool over the last 4 years. We call it simply impedance scan tool. On the left, you see a graphical user interface for this tool, and it interfaces with this yellow boxes. So this is, and this software is based on a PSCAD EMT simulation tool. And what we really need to do is that This yellow boxes is what resides in the PSCAD model, and the GUI interacts with that yellow box. For example, if I want to understand how this PV plant impacts the oscillation modes of a system, then I insert this yellow box between the plant and the grid. Well, the GUI or this software will basically perform the scan of impedance, and it will scan impedance of both the PV plant as well as the network. And then I use that scan data to perform stability analysis. We can repeat this process at other IBRs. Not just a single plant, we can also try to understand using this tool what is the impact of a feeder with 100 DERs on the stability of a wider transmission network. So this gives you ability to zoom in the network because you can really place this tool anywhere. Looking more at like how it looks like in PSCAD. So here is that yellow box that I put in PSCAD. If I want to understand how this particular IBR is impacting the stability of this system, we perform the scan. The output scan data looks like these files that you are seeing on bottom right. And the name of these files are really show what is the frequency of perturbation for which you are collecting the data. And this tool is fully automated. It selects the perturbation frequency, basically the perturbations that you inject. And also I forgot that this yellow box is really internally, it just contains a three-phase voltage source in series. And that is how you inject these disturbances or perturbations so that you excite system at different frequencies. And it also includes voltage and current recorders. So it basically measures the voltages and currents. So the tool is fully automated, as I said, like it selects perturbation frequency, magnitude, recording length, whether you need to record data for 1 second, 10 seconds, it does that automatically. The post-processing algorithm is even smarter. It synchronizes the reference frame of impedances. Remember that the impedance of any three-phase network, like it's a DQ impedance, you need to align the D and Q axis with grid voltage angle. So there is a reference frame associated with that. So the algorithm does the synchronization of reference frame. It optimizes the FFT window. So even if you have, let's say, the data you have scanned or recorded is for 1 second during that perturbation, the tool will select only the perform FFT analysis on a time window to minimize the leakage errors because there are multiple frequencies involved here. There's a fundamental frequency, 60 hertz or 50 hertz. There's a perturbation frequency that you're injecting. There's a coupling frequency. So the tool will basically optimize the FFT window to minimize the leakage so that we get a more accurate scan. And finally, it outputs the impedance in both DQ and sequence domain. Basically, the DQ impedance or positive sequence and negative sequence impedance, as well as coupling between the two. So let me show how it works. Before that, I talked about scalability, how this tool is or this approach is scalable because we, instead of looking at all IBRs together and how they affect the stability when you connect all of them, we are really looking at the question is reverse. What happens if I take out this one particular IBR? So it allows us to understand stability by looking at one IBR at a time and repeating that process in steps. So that is one scalability. The other scalability is that the tool can work with a big system simulated in EMT simulation platform, or it can also work with co-simulation. So here I'm showing this tool really residing in the PSCAD part of the system, but then this PSCAD part of the system interfaces with the PSSC network. So we can combine these strands of PSCAD, PSSC co-simulation or EMT and phasor co-simulation with impedance scan tool to really understand the stability. We are using this to understand impact of in one DOE sponsored project. We are using this combination of PSCAD, PSSC co-simulation and impedance scan tool to understand how offshore wind generation that is planned in the Atlantic region will impact the stability of onshore grid because we have really good models of onshore grid in phasor domain, but vendors will be able to provide good models or models which are accurate even at high frequencies in EMT domain. So we can combine the standards of co-simulation with the impedance scan. So I'll be a bit slow now. I will try to talk about how this tool works really. So this is a 14-bus system with one synchronous generator, 3 grid forming inverters, and 2 grid following inverters. And during some contingency or fault event, we see some oscillations in this system, 2.5 hertz oscillations. The question is how we can use the impedance scan software tool that I just described to understand the stability, how to identify frequency and damping of modes which we are not aware of, how to understand impact and participation of different IBRs on that mode, and also can we estimate the amount of grid forming inverter capacity that is required for stable operation using this tool. So let's first perform the scan. Although here I am showing the block at grid forming inverter at bus 3, first I'll show the impedance scans performed at grid forming inverter at bus 6. So once we do that scan at this grid forming inverter at bus 6, this is what we really get when we apply this tool. We see the network that this grid forming inverter at bus 6 or grid forming plant at bus 6 is seeing, the impedance of the network. And we also measure the impedance of that plant itself or admittance, or they are basically correlated. The real strength of this tool is that by inserting that yellow box, it isolates the dynamics of that plant from the rest of the network. And that allows you to understand how this particular plant is impacting the stability. So we get the scan by performing the scan and then post-processing the data, we get this admittance responses. And then we use that admittance responses to plot what is called modal impedances. And then the peak of modal impedances will give you the resonance frequency, if there are any in the system, and the Q factor, or how peaky that resonance peak is, will tell you what is the damping. As I said before, that by measuring the impedance of the rest of the network and the IBR plant separately, you can really isolate the dynamics of IBR. So here we are showing the modal impedances with IBR and without IBR. The circles, they represent without IBR plant, or basically without this grid forming inverter at bus 6. And this stars, they really show the modal impedance with IBR. Using this modal impedance responses, we see that with the IBR, the resonance is at 2.5 hertz, which is what we also observed in time domain simulation. And without this plant at bus 6, the resonance mode is at 2.36 hertz. And as I said, like looking at the Q factor, we can also find out the magnitude of damping. So with IBR, the damping is 13.3%, and without IBR, it's 5.9%. Without really going into the theoretical details, the Nyquist plot we use to understand whether the damping without the IBR is positive or negative. So to basically give a sign to it, because the modal impedance plot will only give you the magnitude. So if the origin lies within this Nyquist plot, without IBR, the damping is negative. Because we started with the premise that with IBR, or basically the integrated system is stable, we want to understand if we remove the IBR, whether the system remains stable or it becomes unstable. And during this analysis, we find out that this particular plant at bus 6, the grid forming inverter plant, increases the resonance frequency or oscillation mode frequency from 2.36 hertz to 2.5 hertz. And it improves the damping from minus 5.9% to 13%, or basically by 19%. So this is the impact of this particular IBR. And this also shows that if we remove this IBR or curtail this IBR, the damping will become negative. And this is the mode which we are seeing will actually become unstable. So we repeat this analysis at other grid forming IBR, we see similar impact, that this particular IBR at bus 3, which is grid forming, is not impacting the mode frequency that much, but it is adding 21% of damping. So removing that IBR will again make the damping negative and make the system unstable. And that negative sign is again because this Nyquist plot is encircling, or the origin is within that Nyquist plot. We do that with another plant which is grid following, and we find out that because this Nyquist plot is not encircling the origin, the damping without this IBR is positive. So removing this grid following inverter is not making the system unstable, but it is still reducing the damping that we can get from the modal impedance plots. So it is increasing the resonance frequency from 2 Hertz to 2.5 Hertz, which is what we see with the full system. And it is adding damping by 5.75%. This analysis, we found that one IBR at bus 14, which is again grid following, is a negative contributor to damping. So it has a higher damping. The system has higher damping when we remove this IBR. So it's contributing negatively to the damping. So we do this analysis at as many IBRs as you like, and we can find out what is the mode in the system. Here I'm focusing on one mode, but we can perform the analysis at different frequencies depending on what you want to identify. We can find out how these different IBRs are impacting the modal frequency, as well as, more importantly, how they're impacting the damping. And one thing I would like to highlight here is that some system operators I have seen that they consider if the oscillation is high at a particular IBR, they think of it that that IBR is possibly a negative contributor or causing that oscillations, and they try to curtail it. But here, if you see the oscillations are high at bus 6, or basically IBR at bus 6 compared to other IBRs like it this grid following, but IBR at bus 6 is actually contributing positively. So just looking at the oscillation magnitude will not tell you whether that particular IBR plant is a positive contributor or negative contributor, because the oscillation magnitude can be high if the event which is exciting those oscillations is closer to that plant, or it might simply be high because that particular IBR plant is participating more in that mode. But participating more doesn't mean that it's a positive contributor, or it's actually adding the damping. So if we take this brute force approach of just curtailing IBRs where we have high oscillations, sometimes we may actually are reducing the damping and making system more vulnerable to this oscillations. The other thing is the grid forming capacity. So here we have seen that this two grid forming inverters, they are positive contributor of damping. If I remove any of that, it reduces the damping by around 20%. And the damping of this mode is just 12 to 15%. So removing any of this grid forming resource will make this mode unstable. So this in a way gives you a quantity of how much grid forming capacity is required in this system. And not just that, we can also use this to understand how control tuning might impact the system mode. So for example, if I increase the voltage control bandwidth of any of this grid forming resource, basically make it behave more like an ideal voltage source, its contribution to damping will improve. So the capacity of grid forming resources that is required in system for stable operation is also related to the control bandwidths. We can tweak the control bandwidths, and we can change the amount of grid forming capacity required for stable operation. And here I would like to add a disclaimer that whatever I'm talking here is all small signal stability. So let's say the small signal stability analysis using impedance scan tools tells you that you need X amount of grid forming capacity in the system. That might be different from transient stability standpoint, which is for frequency stability or voltage stability. So everything that I'm talking here is small signal stability or control interactions and oscillations. So that's a separate part. Here we just show if we can really operate the system stably in steady state. Now, how it behaves during certain loss of generation, we also need to consider that aspect, just so that people don't think that I'm saying that the grid forming capacity can be requirement for that can be reduced by just increasing the voltage control bandwidth, because transient stability and frequency stability are another metrics that we need to consider. So I think I have another 10 minutes, and in that I would like to cover the impedance measurement system that we have developed at NREL. So this is like a hardware twin of the impedance scan software tool that I just described. We use our 7 megawatt grid simulator to measure impedances of different inverters and wind turbines. Right now, because of the limitation of grid simulator size, we can measure impedance of devices rated up to 7 megawatt, but we recently procured a 20 megawatt grid simulator, which is already here at NREL and which will be commissioned probably early next year. So we'll be able to scan impedance responses of even high power devices. In this impedance measurement system, we inject oscillations or perturbations in the voltages, which we impose at the terminals of the device. We change the frequency of these oscillations that we are imposing on top of the fundamental voltages and see how the device is responding in its output currents. For example, here are response currents from a 4 megawatt turbine, and then find out the transfer function from voltages to current, basically the magnitude gain as well as the phase gain. So, and we do that using our medium voltage data acquisition system, which measures voltages and currents in a which are all GPS synchronized. So they are 50. We measure voltages and current which are sampled at 50 microsecond, and then because they're all GPS synchronized, the jitter is really small. So that is how we get the impedance response. As I said earlier, we are trying to get this test into IES standard for wind turbine testing, so that whenever we are doing tests like a low voltage ride through or how a wind turbine behaves during a frequency event, we should also be performing impedance scans, because that is very critical to understand how that wind power plant will impact the stability of the grid or small signal stability of the grid. This is the impedance scan in action, or basically how it happens for a 4 megawatt turbine. So top left is three-phase voltages at 13.8 kV level, which are imposed on the turbine. And the grid simulator includes not just the fundamental voltages, but also the high frequency or the perturbations, which goes from 0.1 hertz to a couple of kilohertz. The top right is basically the frequency spectrum. So as you can see, the fundamental frequency line, it stays constant. We are not changing the fundamental frequency component. And on top of that, the grid simulator adds this small few percentage of perturbation and changes the frequency. The bottom left is the output current from the turbine for different perturbations, and bottom right is the spectrum of current. So this is how we scan the impedance response. Either it's using this impedance measurement system or in that the software tool that I just described. So what we get from this impedance responses, one is I talked about that we can understand how IBR is impacting the stability, whether it's a negative contributor or positive contributor. The other application of impedance responses is control design, how to understand what different control modes are going to do. For example, grid forming versus grid following, how they impact the system stability. So here are impedance responses of a real 2.2 MVA battery inverter, a 2 megawatt PV inverter, and 2.5 megawatt type 3 turbine. And the impedance responses are shown, basically positive sequence impedance responses, when these devices are operated either in grid forming mode versus when they are operated in grid following mode. And as you can see, within the control bandwidth below a couple hundred hertz, the impedance responses are different because they are dominated by the controls that are inserted in the device. At a high frequency, it's mainly about filters and transformers, so the impedance doesn't change with the control mode. Now, I would like you to focus on the magnitude response first. So for grid forming mode, the device is trying to act as a voltage source, and we know that an ideal voltage source has a zero impedance. So most IBRs, when they are operated as a grid forming mode, they'll have a lower impedance compared to when they're operated in a grid following mode. So we can use those impedances to really define how good a voltage source it is behaving, so define specifications. We can also use it to understand the damping characteristic. For example, here in the phase responses of these devices, I am showing green rectangles, which are basically showing the phase when the phase is between plus or minus 90. So whenever the phase of impedance of any device is within plus or minus 90, it means that the impedance has a positive real part, or it is behaving like a positive resistance and contributing positively to the damping of the system. So And if the phase goes outside of this plus or minus 90 degree, that means the impedance has a negative real part, or it's acting as a negative resistance, and it's basically reducing the damping from the system. So one interesting thing that we found out during all this measurement is that most grid forming devices, either it's a battery inverter, PV inverter, or wind turbine, they have a better damping characteristic. Their phase of impedance stays closer to 0 degree, or basically they stay positive, they behave like a positive resistance in that frequency, and which reduces the risk of all these control interactions, which you can see in this 2.2 MVA battery inverter or 2 megawatt PV inverter. But really the response was really striking with the type 3 wind turbine. Instead of seeing a huge negative resistance that we see in grid following mode, the grid forming mode has a really low, it had a positive resistance. So what we figured out is that type 3 wind turbines are less likely to suffer SSR, which they are prone to suffer if we operate them in a grid forming mode. So this is my last slide. I would just say that impedance scan tools are critical to understand small signal stability of IBR grids. It might be debatable whether we use them for all types of small signal stability issues, or we still depend on standardizing controls for slower control interactions where it is possible to standardize certain things, but we'll still need them for a little bit higher frequency, about 5 or 10 hertz, where it is very hard to standardize controls and also to model them, because it really the control codes are driving the behavior, not physical equations, as in the case of synchronous generators. I talked about all this part. The last part, one application that I did not talk about, is online estimation of system inertia in a non-invasive manner, and which is what we have done at NREL for a real 2 megawatt synchronous generator. And in terms of the ongoing developments, we are trying to reduce the time it takes for impedance scan and post-processing of scan data, developing methods to estimate impedance from just real measurements from fault recorders and PMU, so that in future, I think we are getting a lot of data. So I would imagine a future where we can use all this data to get impedance responses at different nodes in the system, and system operator can see in real time, like what are the oscillation modes in the system which are arising with different changing operation conditions, and how its damping is changing, so that they can take actions in real time before there is any oscillations or stability event. And last is selection of perturbation intelligently, so that we have a better signal to noise ratio. So with that, I would like to acknowledge the entire team, which has been working tirelessly for the last 4 years on these tools, both the impedance scan software tool and impedance measurement system. As you can know, that this requires development in control theory, the signal processing, software, graphical user interface. So a lot of work has gone behind it, and of course, this is a team effort. So thank you to everyone, and just acknowledging their contribution. So that is the end of the slide. Sorry, I went a little bit fast and I had to cover so many things, but thank you so much for your attention. You're on mute, Julia.
I'm on mute, yes. Thanks, Shahil. We'll get to questions. I'm sorry. So the first very popular question is on slide 9. Is it not a big assumption in the reversed approach that starting point is a stable system? It means system with IBRs is initially stable.
So here's the thing. So when you are connecting the IBR to a stable grid, then you use the standard approach, where we are trying to find out how this new IBR, which is coming into system, is impacting the stability. So that is the standard approach when you connect the IBR. But when all the IBRs are already in the system, they are already operating in a stable manner, and now you see some instability. We are not going to start understanding, analyzing the system which is unstable, because we can't really perform an impedance scan. We are always going to analyze system which is stable and try to understand, hey, what are the modes in the system which are underdamped, and some even probably just excited that mode. So we will always start from a stable system when you want to consider multiple IBRs which are already there in the system. So that way it's a reasonable point to start with.
And when you say start with a stable system, you say you're assuming that it's stable and then start removing IBRs and looking at impact?
So we assume that oscillations that we saw in field or EMT simulations, they were excited by some event, but that mode is already there because so we start with a system which was there just before that oscillations occurred. And so even though the modes are already there in the system, it's just that they were not excited. So we start from that system, which is, if you look at my cartoon, is like system is at the cliff of instability, but still it is not stable. And we start from that point.
Right, thanks. In your experience, how sensitive are impedances to operating point, and how do you account for saturation when operating close to full injection?
That's a great question. And the operation point affects the impedance around the fundamental frequency if you're looking in the sequence domain, or around 0 Hertz if in the DQ domain. So if I want to understand oscillations below 5 or 10 Hertz, I would be super careful about the operation point that I'm considering. But as you go at high frequency, about 20 Hertz, the operation point doesn't really impact impedance that much. The second question is about the saturation. So these are small signal analysis tools. So when we perform scan, we make sure that we are not exciting any nonlinearities. We design our perturbation levels so that they are high enough so that we have high good signal to noise ratio, but not high enough that it is exciting all those saturations and nonlinearities.
And then at those frequencies, you said 9, 10 Hertz, where it would depend on operating point. What would you recommend doing?
During that, first is we start with the operation point where we had this oscillation problem, and then make a map of like few operation point around that region and try to understand how the stability is changing with that operation point. So there we need to consider several operation point. The good part is that at low frequencies, you can get impedance even using just transient data. Just create a step change in the load and use that data. So that way you can have a fast impedance scan. So we are still working with that aspect.
Thank you. Is the impedance analysis tool available for everyone? And if yes, where can we download it?
So we are right now working with 2 to 3 system operators to use this tool to understand oscillations they have seen in their system, also with a couple of vendors. Right now, the tool is not openly available, but if you see oscillations or if you're concerned about that in your system, we can license you the tool. The NREL can license that tool for free, and we can work with you. The reason we are not releasing it as open source right now is because it's still a little complicated. It's not user friendly. Like there's like codes all over the place. But our hope is that by the end of next year, we'll release this with detailed manuals in a public forum.
Right, thank you. The next one is more of a comment. IBRs have transitional controls, adaptive control response to small signal, nonlinear large signal response. So you still need time domain to support solutions.
Time domain is super critical. This is just when you see oscillations in time domain and you are not able to understand who is causing that, what IBRs to curtail. So this is like not replacing time domain simulation, because ultimately the tool is developed on PSCAD, right? So time domain simulations are super critical. This is just adding value where you don't understand things from time domain simulations.
All right. Another question about operating point. Could distributed real inertia, not virtual inertia, be deployed to improve grid system stability in high IBR scenarios?
I think the distributed inertia can help, and the tool that I described about online estimation of inertia, one research aspect that we're exploring is how the location of inertia is going to affect the impedance. So this is beyond the purview of impedance scan tool. Yes, tool can be used to understand stability with concentrated inertia versus distributed inertia. But we are not really researching how distributed inertia will impact. This is just about using the tool to understand stability, which can be for anything, like whether you have inertia or not.
How much costly in terms of time is this analysis? How many AC cycles do you need to consider to compute each point?
That's a great question. And for low frequencies, because you need to have a high resolution, so it might take 3 to 4 hours for doing impedance scan at one IBR plant. If your oscillation frequency increases, that can reduce to around half an hour or even 15 minutes. So we are talking about roughly from like half an hour to 6 hours at this point. And we are working on it to reduce the scan time and post-processing of time.
Right, thank you. For a system operator without this impedance scan tool, how can they assess which IBR is going to impact positively and which going to impact negatively? The stability, I guess.
I think it's just like performing bunch of time domain simulation, remove the IBR, curtail the IBR, and see how it is doing it. So do lots of IBRs. I don't think there is an organized way to do that, and there is a reason for this impedance scan to be there. But yeah, just performing lots of time domain simulations with different operation conditions and control parameters of IBRs.
Right. The next is comment on the question. Shahil, your impedance measurement method is very useful. In particular, have you used it to verify behavior of EMT models supplied?
Yes, I don't have a slide here, but we scan impedance of few inverters and a 4 megawatt wind turbine to match the, and we have both systems, right? The impedance scan software tool and a real impedance measurement system. So we compared the real impedance measurements of a 4 megawatt turbine with its EMT software, like the real code model that was provided by vendor. And yes, we have done validation and given feedback to vendor on in which frequency range the model is not accurate. So we have done few validation of EMT models.
Mm-hmm. Yeah, the next one is, I think you already answered it. Also, have you tried outside of lab to achieve the same impedance measurement for in-service measurement? This should be possible and helps track control changes.
So we have, then the general strategy has been that once the impedance is measured in the lab and it's the EMT model is validated, we just rely on EMT model to see how the control change is going to impact the impedance. So we don't do impedance measurement again and again whenever there is any control change by vendor. That has been the strategy till now with a couple of vendors with whom we are working.
Mm-hmm. The next question is, I think it's to your one of the first slides that you had with different oscillations. Any idea the systems had weak short circuit strengths to start with?
Many of them were with a weak short circuit strength. A few others were with series compensated transmission line. And then a few were about really the interaction between two power electronics devices like offshore HVDC converter and a wind power plant. But yeah, that's right. The weak grid is one of the issues. But then other times is when you have like a offshore HVDC converter and wind plant where you have just two power electronics devices interacting against each other, where you don't have any real grid.
Right. The next one just popped up because somebody voted it up. Can you clarify why you don't use traditional eigenvalue analysis tools for stability analysis of IBR?
I think, yeah. So in the tool, we started with getting the eigenvalue analysis, like using these impedance scans and performing curve fitting to obtain the eigenvalues. But we realized that it has a drawback. We don't want to go from measurements back to the model. Like to put it very simply, if your two impedance response points are two frequency, you can curve fit it by infinite number of lines, right? How you curve fit it. So getting those models through curve fitting will result in artificial eigenvalues, which are not actually there in the system. And it creates all this type of artifacts of curve fitting. We want to avoid that. We want to start with measurement and just stick with the measurement. And that's why we don't go to eigenvalues. If we have a models, which we know that we don't get equation-based models for IBRs, then of course eigenvalues can be used. But the IBR dynamics are so complex that we have to forget about the world where we can describe them by, I know some people may not like this, but we have to forget about the world where we can describe IBR dynamics by 10 or 15 differential equations. It might be possible for slow dynamics, which are occurring at less than 10 hertz, but if you want to consider the full spectrum, it's just not possible. You can't convert 1,000 lines of a C code into 10, 15 differential equations.
I'll ask the last one. I think it's an interesting question. We'll wrap up after that. Can we determine frequency response shape as a requirement for new IBRs to guarantee that system will be stable, like response time and damping of steps?
Yes, we can do that. And if we know the system characteristic at the point of interconnection, we can do that. I don't recollect the name of a standard, but there's a standard in Switzerland to avoid this control interactions in electric traction networks, where because they have a long overhead cables which keeps on, like depending on the position of train, the impedance of grid keeps on changing. So they find out where are the resonance modes in that system and then enforce impedance characteristic requirements on the electric locomotive. So yes, that type of standards is possible. Right now they are developed only in like a highly power electronics based system like offshore wind energy systems or electric traction networks, but I I do foresee that we'll have some similar standards even for wider transmission systems.
Right, thank you. So, okay, well, at the top of the hour, so we are going to need to wrap up. Shahil, thanks once again for interesting presentation. I learned a lot, and I hope the listeners did too. As I mentioned earlier, an email will go out once video file has been posted, and we'll get the responses for all your unanswered questions posted as quickly as possible. We appreciate your engagement, and if you would like to stay engaged, I would invite you to participate in the next G-PST ESIG webinar on July 12th on wind and solar power forecast management. Further information on all ESIG webinars can be found on our website, www.esig.energy under events. And you all are invited to attend. Information on all G-PST webinars can also be found on www.globalpst.org. Shahil, I wanted to thank you once again for this very timely webinar, and thank you all for your interest. We look forward to seeing you again in the near future. And in the meantime, take care, stay safe. Thanks again for participating. Goodbye.